video. In today's video, we're going to discuss how to use the confusion matrix in order to calculate different performance measures such as precision and recall. Before we get into this video, make sure to subscribe button down below and like the video for more content just like this. All right, let's discuss here cross-validation predict and compare it with cross-validation score. So in previous tutorials, we discussed what cross-validation score is. So cross-validation score is basically when we split a model into some number of k folds. And then from there, we were able to train the model on roughly k minus 1 folds and test the model on the kth fold. And we were able to alternate which folds we used for training and which fold we used for testing. And what that enabled us to do was it enabled us to test the model on a different on a different fold every single time on new unseen data that the model has not yet seen. And so it was very good for us and was able to give us some performance measure, whether it be the root mean squared error score or an accuracy score. Now, what cross-validation predict allows us to do is cross-validation predict allows us to perform basically the same operation, but for every time we predict what the value is going to be, we're going to be able to get the prediction as being our return value. So instead of us comparing what the results should have been versus what the result was and calculating some percentage of accuracy, we're able to just simply output what the model predicted, what our SGD classifier was able to predict. And based on that, we can then determine how accurate that was relative to the actual values that the model should have predicted. Okay, so we're able to get the prediction for the that the model predicted. Now, keep in mind, these are not the actual values that we should have. These are the predictions that the model made based on the k minus 1 folds that the model is trained on, given that we have k folds. All right, and those k folds, remember, are assigned by our CV parameter, which states the number of folds that we want. So you're seeing here that we have the code right over here. So we import cross-validation predict from the model selection module in scikit-learn. And then from there, we call cross-validation predict. And then we pass in SGD classifier, which we've already created in the previous tutorial. We then pass in our training set. We pass in the Y values, which are basically the target values for our training set, which what the model should be predicting, the actual values. And then we pass in the number of times we want to train the model and test the model. And so then we output that there, and we see that we also have the shape of the model, shape of the output rather, as well as the individual outputs. So keep in mind here that the number of outputs is actually equal to the length of the training set, or in other words, the length of the output set. And the reason for that is because keep in mind, let's say we have in this case 60,000 rows in our training set. What we're going to do is we're going to split that into 3 individual folds. So 60,000 divided by 3 is 20,000. So we're going to have fold 1, which is 20,000 instances, fold 2, 20,000 instances, and then fold 3, which is also going to be 20,000 instances. And then from there, once we have those individual instances, we're going to train the model, let's say, on the first 2 folds. Well, if you train the model on the first 2 folds, given that each fold is 20,000 instances, you're going to be training the model on 40,000 instances. And then you're going to test the model on the third fold, which is the remaining instances there. So the remaining 20,000 instances in the other fold. So for every time you're testing on roughly a third of the data set, right? Since CV is equal to 3. We're going to be testing on a third of our data set. How many times? 3 different times. So 1/3 times 3 is equal to 1. And in this case, 1 represents the percentage or the decimal percentage, I guess you could say. You could convert it to 100%. The percentage, in other words, of the training set that we're going to be able to get. So 1 times 60,000 is 60,000. So your output is going to be exactly the same as the number of data instances in your training set. All right, so that's kind of the reasoning behind that. Okay, so hope you were able to understand that. If not, you can try to run the code, and then you'll kind of be able to reason your way through this. Okay, so all right, so let's go ahead and move forward now. Let's discuss here why this is helpful. First of all, why this is helpful. So why is the cross-validation predict helpful for us? The reason why is because we're going to be able to do a lot more with our predictions compared to what we did before. Because remember, cross-validation score, which is what we've been using up to this point in previous tutorials, that simply tells us the percent of accuracy or the root mean squared score or something like that. But if we know what our individual predictions are, we're able to do a lot more with those individual predictions. We can calculate, for example, of the instances that are true, that are actually true instances, how many of them did the model predict as being true? Of the instances that are false instances, right? How many of them did the model correctly identify as being false? There are so many different things that we can do with this result set, okay, compared to if we just get a percent accuracy score. Now, a percent accuracy score has its use cases. When we were working, for example, with our housing data frame, using a percent accurate, using something like a cross-validation score might have been very helpful. But in this case, one of the reasons why it's not very helpful is because, remember, our data set that's going in as our input are values between 0 to 9. So that means that our model can predict 1 of 10 values. And so that means the probability that the model is going to be incorrect, given that it randomly outputs target values, is going to be basically roughly 10%. So basically, if the model just randomly selected output values, the probability that it would be incorrect is roughly 10%. And we discussed this in the previous tutorial, why this probability is so low. And that's why when we tested our model, I believe we got a cross-validation score of 96% roughly. And that might look like 96% is a very high accuracy level, but in reality, that's not really that high of an accuracy level, because of the fact that if the model just randomly predicted values, we would basically have roughly a 90% accuracy in the long run. So 95% accuracy is not very high or as grand as it might seem. And so because of that, if we know the individual predictions that the model made, we're able to get more meaningful performance measures, which the goal of any performance measure is to provide meaning behind it. If a performance measure has little to no meaning, then it is not very valuable. The greater meaning that can be attached to an individual performance measure allows us to be able to fine-tune the model in a better way, especially as it relates to fine-tuning, right? And so we want to be able to fine-tune our model correctly, so we need meaningful performance measures. And being able to get a result set as such, so simply choosing random outputs and evaluating our model on those random outputs is not very good, because if all the model is really doing is just assigning random outputs, then you don't even need a model at that point, right? You can just code a simple small Python script which just outputs random values from 0 to 9, right? Like that isn't really complicated if that's all your model is doing. So again, that's not very useful. Okay, so by knowing these individual values, we're able to get much more. Okay, as far as accuracy measures. All right, now with all that being said, let's now go to a confusion matrix. So a confusion matrix is something that will help us along this path of being able to get meaningful performance measures. So I have a picture here. This is basically a picture that I got from a website here that I have at the bottom. And so you can go and take a look at their website as well. I'll put the link in the description below. But you can see here, this is basically what a confusion matrix looks like, theoretically that is. Okay, so you can see that you have basically what looks like a Punnett square. In biology, it looks kind of like a Punnett square to a certain extent, but this is not a Punnett square. So this is basically a predicted versus actual arrangement here. So what we see here is that we have Tn, Fp, Fn, Tp. What exactly does this stand for? So Tn stands for true negative. So what true negative means is basically the model correctly identified something as being negative. In this case, negative means something, in our case, as being not 5. So the model correctly identified something as being not 5. That's all that it means. Fp means false positive. The model incorrectly identified something as being positive. That means the model incorrectly identified something as being 5. False negative is, Fn is false negative. False negative means the model incorrectly identified something as not being 5, as being false, which means the model incorrectly identified something as not being 5. If the model incorrectly identified something as not being 5, what is the value actually? Well, that means the value was 5, but the model identified it as being not 5. Okay? TP stands for true positive. What is true positive? True positive stands for, basically the idea behind this is the model correctly identifies something as being positive. Okay? So this is what a confusion matrix is going to return for us. It's going to return for us this, and you can see here this output here. This is basically how the output's going to be like. So you can see there, it's basically just an array of arrays, or a list of lists, I guess you could say, where you have a list, and each of the elements are lists, and each individual list, the first list is going to be our first row, the second list is going to be our second row, as such, all right? So this is how it's basically going to be like. Now, taking a look at this, can you notice some things about the row relationships? Look at the row relationships. So notice here that it says true negative. The model correctly identified something as not being 5. False positive. The model incorrectly identified something as not being 5. Incorrectly identifying something as being 5 means the model incorrectly identified means the value is actually not 5. So in both of these cells here, you can see that the actual value was negative. In these two bottom row cells, false negative, the model incorrectly identified something as not being 5, which means the value is actually 5. True positive means the model correctly identified something as being 5. So the value was actually 5. So you see that in the bottom row, the value actually was true, or was 5 in this case. In the top row, the value was actually negative, or in our case, it's going to be actually not 5. Okay, so yeah, actually not 5. Okay, good. So that is basically something you can notice there. What else can you notice? Well, notice the colors here. You have blue, and then you have yellow. This is another thing that you can notice a correlation, and that's why having all the data predictions is so valuable, because we're able to find all these different relationships that we weren't able to find previously when we had cross-validation score. But just keep this in mind here. So we have true negative and true positive. This is basically when the model correctly identifies something as being false or being negative. The model correctly identifies something. The model correctly identifies something as being positive. If we add these two values together, that's basically going to tell us the number of times the model correctly identified something. Okay, correctly identified something as being either not 5 or correctly identified something as being 5. So if you add those two values together, if you add these two values together, what's the exact opposite? The times the model was incorrect in its prediction. So the time that the model incorrectly identified something as being 5, or the number of times the model incorrectly identified something as being 5. So you see that there. So if you add these two values here, you're going to be able to get basically the sum of the incorrect values that the model had. Okay, so with that, you can actually perform in many ways different operations. So another operation that you could do is you could figure out, okay, now that I know all these different relationships, what percent of my values are actually true, or are actually positive? Well, how would I do that? Well, we know that we have positive values here at the bottom, and we have negative values here at the top. These are the values that are 5. Okay, these are all the values that are 5. If you take this value, right, divided by the value of this plus the row at the top, you're going to get the percent of values that are actually true. And then if you take that number and have it minus from 1, right, then you're going to get the values that are actually not 5, which are actually negative. So that's another thing that you can do. And that will give you, by the way, it can tell you how randomized your MNIST data set is, right? In our case, what should we want that value to be? Well, we would want the number of values that are positive. If we add these two cells up, and if we perform the division, we would expect that value to be less than or equal to 10%, or less than or equal to 0.1, because according to the law of total probabilities, we would want roughly 10% of our data instances to fall in that category. Okay, according to the law of total probabilities. So there you go. Those are different things that you can do there. All right. So that's some of the stuff there. Now let's talk about how you can get this. So the confusion matrix, you can import that from the metrics module in scikit-learn. And what you can do there is you can pass in the training data, the Y training data, and also the Y training predictions. So this is what the model should be outputting versus what the model actually outputted. So what the model actually outputted is Y underscore train underscore predict. So this is our confusion matrix. All right. So again, I already explained all these things before, so I don't want to go over it again. But again, if you want to look over this, just you can look at this square, and you can identify all the relationships. Okay. So with that being said, let's take a look at another observation. We could technically make all the outputs perfect, right? If we just set our predictions, right, as being equal to what the values should be, and we pass in those two values as being exactly the same, notice how we get 0 and 0 in the diagonal here. So in the diagonal, false positives and false negatives, nothing is incorrectly identified by the model. The reason for that is because we passed in the correct outputs, the actual values for our predictions. Okay, but you can see that if we add these two values up, what should we get? Well, since we got 0 values as being incorrectly identified, the values when you add these two values up should be the total number of instances in our training set, which is 60,000. And if I were to do that, that would add up to 60,000. I'm just looking at it right now. Yeah, it would add up to 60,000. Okay, so that's what you're able to do there. Now, talking about these different performance measures that we can derive from the confusion matrix. So one of them is precision, and we're going to be spending actually the next tutorial talking about precision and recall, because these are two very important different performance measures. But for now, we're going to talk about it highly theoretically, and do some application with it as well. So what precision allows us to do is it allows us to find the percentage of results identified as correct that are actually correct. Okay, so what precision does is that if a result is identified as being true, is it actually true? And we're able to identify the percent that was identified as true and was actually true. And there's an equation for this here, but it's very intuitive in that it's very easy to understand this, okay? So the percentage of results that are identified as correct that are actually correct. So you see here TP divided by TP plus FP. So TP is basically this cell right over here. So it's the predictions that were correctly identified as being true, okay? Correctly identified as being true. So it was correctly identified as being true and identified as correct or actually correct, okay? So that's TP. And we divide that by the total number of TP plus FP. So FP is the instances that were incorrectly identified as being true. So if you add up here all the instances that the model predicted as being true or positive, it would be FP plus TP, right? The model at least predicted it as being positive. So that's what it is. Now, what percent of them were actually positive? That would be TP, or true positive. And so if you do that, you're able to get this equation. And one of the benefits of the confusion matrix is it's very easy to kind of visualize this. So if you want to know the number of instances, for example, that were actually negative, you see here, just add Tn and Fp. Number of instances that were actually positive, Fn and Tp. Number of instances that were predicted as being negative, Tn plus Fn, right? So you're able to get that very easily. So that's how you're able to get your precision. Now, what's a problem with this with this idea here? Let's say the model only predicted one instance as being a positive. If it only predicted one instance as being positive, okay, and predicted everything else as being negative, okay, that would be obviously incorrect in our case, right? We would want roughly 10% of the instances, roughly, to be predicted as being positive, right? And we want 90% of them to be negative. But let's say it only predicted one of the instances as being positive. Now, how many should it have identified as being positive? Well, 10% of 60,000 is 6,000. So it should have identified roughly 6,000 instances as being positive, but it actually identified only one instance as being positive. And let's say that that one instance that it identified as being positive fell under TP, so truly positive. How many false positives are there? How many times does the model incorrectly identify something as being positive? 0 times. Technically 0 times, because of all the instances that were supposed to be positive, that were actually positive, it predicted only one of them as being positive. So that means 5,999 instances that were actually positive were predicted as being negative, were predicted as being negative. But if we take a look at the number of instances that were incorrectly identified as being positive, 0 of them. So if we substitute that into our equation, we're going to get 1 over 1 plus 0. That's going to be 1 over 1, which is 1, which is 100%. Okay, so our precision is going to be 100%. In reality, our precision was very low. We incorrectly identified only 1 out of 5,999 instances. Okay, so that means that we only identified 0.02% of the instances that were actually true as being true. Yet our precision level was 100%. Okay, so there's kind of like a trade-off, if you will, with identifying something as being precision. Because in a normal data set, precision would give us some indicator of how the model is doing. But in a worst case scenario, precision would not give us a very good analysis. In reality, it's not going to be 1 most of the time. That was just an extreme worst case scenario. I mean, it could technically be 0, but let's just go ahead and say, for example, to give a normal example, let's say 1,000. That means that only 16% of the instances that were actually positive were identified as being positive. But the model, the model basically didn't work there because it incorrectly identified 84% of the actually positive ones as being negative. Okay, so that's why it's not necessarily a good performance measure in that respect, but in a different respect, it is, right? And so that's the trade-off that you have to understand there. All right, so the next one is recall. So recall balances off the trade-off that precision has. So there's a drawback to precision. Precision has that drawback of if we do not identify that many instances as being positive, then it'll look like our precision level may be higher than it actually is, right? That's a drawback of precision. Whereas recall avoids that drawback. It actually it counteracts for that drawback, if you will. All right. So what recall does is it allows us to identify out of all results which are correct, how many were identified as being correct. Let me just change that spelling there. All right. Out of all results which are correct, how many were identified as being correct? So this is actually interesting because remember, precision did not had a drawback in this instance. So out of all the results which are correct, how many were identified as being correct? in precision, even if a lot of instances were correct and only a small of them were identified as being correct, we could still get a very high precision level. Whereas in recall, we compare the number of instances that were identified as being correct to all the results which are actually correct. Okay, so this is the equation: TP over TP plus Fn. Okay, so true positive divided by true positive plus false negative. So with this one here, we get TP, the number of values that were correctly identified as being true, over the number of instances that were correctly identified as being true, plus the number of instances that were incorrectly identified as being false. If something's incorrectly identified as being false, that means that it's actually true. Okay, so by doing that, we're able to counteract for that difference. Okay, so if we do that there for our confusion matrix, just to show you a real world example, if we were to perform this calculation, we see that our precision is 83%, okay, a lot lower than the 95% that we saw before, and our recall is roughly 65%. Okay, so 65%. Now, recall there was pretty low. If you take a look at it, what does this actually mean in practice, right? Well, it means that we predicted many of the values, not many of the values that we predicted as being, many of the values that we predicted as being negative, some of those values actually were positive. Some of those values were actually positive. And so because of that, roughly 35% of the values that were actually positive we identified as being negative. Okay, whereas we should have been able to include that in our true set, in our true prediction set. So that's a very low prediction accuracy there. And then for precision, in that regard, basically what that shows is that 83% of the instances that we identified as being correct, those were actually correct. So of the instances that we identified as correct, only roughly 17% of those instances were actually in the false category. Okay, so that helps us to be able to understand that. And again, this is much lower than the 96% accuracy that we saw in the cross-validation score. Okay, so that's that was a longer lecture or a longer tutorial, and so that's the confusion matrix there, as well as precision and recall. In the next tutorial, we will discuss how to use these with regards to their individual models. So scikit-learn does have models for each of these in terms of being able to do this without us necessarily understanding all the math behind it, but it is still important to understand all the math behind it because understanding the math behind what we're doing is very important. All right, so I will see you in the next tutorial.